For right now, what I want to do is I want to introduce you to the concept of forces and force vectors. And I'm going to introduce you to a tool to make your force vector diagrams. They're called free body diagrams. Now, I get to be a bit of a stickler on these diagrams because if you do them right, it makes the problems really easy to solve, the force problems easy to solve. If you do them wrong, you have no idea where you're going. I used the analogy yesterday when some people came in to ask for help on the homework. I said, a number of you come in, you start working a problem, and the first thing you want to do is grab your calculators and start mashing buttons. Think of this like going camping. When you go camping, the first thing you do is not going to be roll out the sleeping bag. Okay, that's the last thing you do, right? Okay, the first thing you do is you prepare the campsite. So in this case, we've got to do the prep work on our problems in order to solve them. Okay, now before we get started on that prep work stuff, let's go ahead I use the royal we. We are going to discuss, which means I'm going to tell you, about forces. What is a force? Not what is the force, what is a force? Yes? A push or a pull, that's it. We can go a little bit more detailed on that, but for our working purposes, a force is any push or pull. This leads us to something very important, which is, one, forces are vectors. They have direction, because pushes and pulls have direction. Take a look at a tug of war, right? One team is pulling in one direction, the other team is pulling in the other direction. But also important is that forces are interactions between two objects. If I've got a push or a pull, let's say I've got a tug of war, let's say I've got a push, somebody's leaning up against a wall, okay? If an object is being pushed, there's got to be something doing the pushing. You see where I'm going here with that? So there's got to be two objects involved in a force interaction. The object that the force is acting on and the object that the force is being imparted from. If you don't have two objects, you do not have a force. It's that simple. Okay, our unit of measure is going to be the Newton, named after the small, no, not the small scientist, it's named after the small fruit-filled cake. Right? Okay. I had a little bit of it, and the unit of a Newton is defined to be 1 kilogram meter per second squared. Now, as you saw in lab number 3, there seems to be a relationship between a force and an acceleration. We saw in lab number 3, investigation 2, that as you increase the force, the cart increased in its acceleration. So there seems to be a relationship there. So let's go ahead and use that, and we're going to derive our unit of measurement. The unit of the Newton is going to be derived as 1 kilogram accelerated 1 meter per second squared. Okay, that makes sense, right? Now, I had a little bit of an epiphany moment a few years back, which went nowhere, but it was still kind of interesting. I was looking, again, my little joke about Newtons are named after the small fruit-filled cake. The light bulb came on. What if the weight of a Newton was a Newton? That would have been too literal for words, wouldn't you think? The force of gravity pulling down on a fig Newton would have been 1 Newton. So I went ahead and I did an experiment. I went ahead and got some fig Newtons, took their masses and figured out their weights, and it turned out no. No, you need about maybe 25 fig Newtons to have the weight of a Newton. But still, I just thought it was kind of a oh wow moment, right? Okay, let's talk about something real simple. Namely, if a book is lying motionless on a table, what are the forces acting on the book? Now, I'm not asking you to answer that question right now, but that's a question we're going to be asking over and over and over again. What are the forces acting on an object? I'm just using this as an example. What are the forces acting on an object? In order to answer that question, we have to really ask two questions. The questions are, what is interacting with the object? In other words, what is providing the force? And what is that type of force? What is the nature of the force? I got a question in the back. We'll talk about that in a moment. As I said, I'm using that question as an example to go with the bigger question, which you're going to see all the time. What are the forces acting on a body? What are the forces acting on a barge? What are the forces acting on a tire? What are the forces acting on a basketball? You're going to get those types of questions over and over and over again. So what you need to do is you need to identify what is interacting with the body and what type of force is that being provided. You following along now, guys? Okay. As my example, let's look at this. We have our diagram, our table here. What we got is our college physics textbook sitting on top of a table. What are the forces acting on the book? We know that the Earth is going to interact with the book, just because we're here and we're not floating off into space. We know the Earth is pulling on the book, and the type of force is gravity. So when I ask you, what's the object? You would say, it's the planet. Anybody who says, oh, what's the object acting on the book? Oh, it's gravity. No, it's not. Gravity is not the object. Gravity is the force. Oh, and by the way, we have a name for it. We're not going to call it gravity per se, although it certainly is true, it is acting on it. We're going to call it weight. Weight is the magnitude of the gravitational force acting on a body. Okay? I only see a half dozen people writing when I did that. Weight is the magnitude of the gravitational force acting on the body. Now, as you can see, the gravitational force is pulling the book downward. So we're going to draw a vector, a force vector, which is pointing downward. And we have to label this. Because remember, we're going to be doing vector math, vector addition, multiplication, etc., so we need to have the diagram. So we're going to put a vector W, that is a W with an arrow over it, to represent that is the object's weight. Following along? Okay, now what's the next object interacting with the book? Yeah, it's the table. So we identify that the table is providing a force, and this force is a support force. Because if the table wasn't there, the book would be falling. Well, the table is there, the book is not falling, so therefore you must have a force that's opposing the weight. That support force we're going to call the normal force. And the normal force is pointing directly upward in this case. Let me rephrase this. The normal force is always going to be drawn so that it is perpendicular to the surface providing the support. That's why it's called the normal force. Normal is a mathematical term meaning perpendicular. So if I have an object, let's say I have a ramp, and I have an object on the ramp like that, then the normal force is going to be drawn perpendicular to the surface of the ramp, like so. You following along with me, guys? The normal force is always perpendicular to the surface. Okay, now, do we have forces here on this book? Is the book moving? So what's the acceleration of the book? 0. As we saw in lab number 3, if we don't have acceleration, we don't have a force. Well, here's the big thing. I'm not saying we don't have forces. We have forces. Absence of a net force of 0 does not mean you have no forces. A net force of 0 means all of your forces are canceling out. That when you add up all of those force vectors, you get 0. Does that make sense? We'll talk more about that next week when we start doing net force diagrams. Okay? So the tool we're going to use is a tool called, let's see, wait a minute. There we go. Before I get to the tool, we're going to categorize forces. There are 2 types of forces. Okay? The first type of force is the kind of force that we're all familiar with. What happens when I grab onto something and pull it? What happens when something pushes on me? Playing football and a linebacker hits me on the hip. What do we have? We have contact. And a contact force is that familiar push or pull, right? So, one good rule of thumb is if two objects are in contact with each other, it's very likely that there's an interaction between them. It's very likely that there's a force between them. The example of a contact force we had already is that normal force, that support force. That's an example. There are others, and we will show them as we go along. Okay? So contact forces are one category of force. Of course, we got another category of force, the non-contact or action at a distance forces. These are forces where, for one reason or another, an object has a force exerted on it, but there's no physical contact between that object and the object providing the force. The best example, the one we're going to see all the time this first semester, is gravity, because the planet is going to pull the object. Okay? So, if objects are in contact with something else, then there's probably going to be a contact force. If an object is on a planet, there's probably going to be a weight force somewhere. Okay? So, unless I say discounting weight, or out in deep space or some other thing, we're going to have weight, and we're going to have to take it into account. All right. This is the reason why this is going to be a really lazy day. I'm going to give you an exercise today. We're going to draw what are called free body diagrams. Free body diagrams are simply diagrams that show the forces acting on a single body. Okay? Some of you have done these before. Most of you probably don't do them right. Not a fault, it's just the fact that to do them right, if you do them right, it makes your math, your equations a lot easier. If you do them wrong, you kind of get lost. Okay, so here's how we do it. Again, the definition, it shows all the forces acting on an object. Number one, what is the object of interest? You take a look at a roller coaster on a track, and it's going through a loop-de-loop, and you got a bunch of people in the roller coaster, and they're all screaming, and it's moving along, and the birds are flying, and all that. You know, what's the object of interest? Well, how do you know? How do you know it's the roller coaster? I could be asking, what are the forces acting on the track? You got to look at the problem. You see? Because if I'm interested in the motion of the roller coaster, yes, I do want to know what are the forces on the cars. But if I'm interested in the stability of the track, I'm looking at the track. What are the forces acting on the track? You following along with me? So you got to take a look at what the problem is asking for and decide what is the object of interest that the problem is looking at. Okay? That's the first thing. Once you isolate the object of interest, the next thing you want to do is identify everything that is interacting with that object. So in the case of the roller coaster, we can certainly say the track is interacting with the carts. Okay? But the air is also interacting with the carts. Earth is interacting with the carts. Can you have a roller coaster in space? No. You can't have a roller coaster in space. There's no gravity to pull it down. That's what's driving the roller coaster in the first place, right? Okay. By the way, a little bit of an aside. A little bit of an aside, and my apologies if you're looking at this, you can skip it on the video. Oftentimes I go to, I've done this before, take the movie Armageddon. You remember the one, Bruce Willis, Ben Affleck? Okay. And I watch that movie and I jot down everything they got wrong from a science standpoint. Actually, I don't do that. Some guy has already done that. He's got a website called Bad Astronomy, and he did that a long time ago. And it's bad. It's bad. That's all there is to it. Okay. But one of the things that gets me, one of the things relating to what I was talking about, influence of gravity and stuff, is if you recall in the movie, there is a scene. The first scene is that they arrive at the space station Mir, and the space station is hanging in space, 0G. Then they arrive, and then once they dock, they then turn on the rocket motors to get it to spin. In fact, I think what they did was they started it spinning and then docked, which really was another stupid thing. But anyway, so then they got it spinning. Now, the obvious reason why they got it spinning was because they didn't have a budget to simulate 0G in the movie. So they had to try to justify gravity on this space station. Okay, all right, I'll suspend disbelief. Later on in the scene, there's the big fire, the explosion, and you got the two guys, the cosmonaut and the astronaut are stuck on the wrong side of the door, and the fireballs are coming. He says, quick, we must go through this passage. It's super cold. Hold your breath, or you will freeze your lungs, which, again, I have a problem with the structural things. But here's the thing I'm relating to this. When you go through it, did you notice there are icicles? As they go through that passage, to show that it's cold, there are icicles in the passage, right? It's a space station in 0G. How do icicles form? That's one of the little details that you kind of go, okay. This is one reason why physicists don't like watching movies like, well, no, we like sci-fi. I love sci-fi. Most of us are inspired by sci-fi. But there are times when the suspension of disbelief gets beyond repair. It's kind of like how aviators watch Top Gun and go, no, just no. I mean, I love the flying scenes. It's a great movie. Well, it's an okay movie, but I love the flying scenes. But there are so many things that Maverick does in Top Gun that would have had him canned before he even had a chance. You know, he's like, land the airplane, go see the squadron commander, and then out the gate, and you're never coming back, kind of canned. Okay, and I'm not talking about the scene where Goose dies. I'm talking about all this other stuff. Anyway, enough of the tangents again. My apologies. If you can go ahead and skip over all that stuff on the video. Let's jump into this. Isolate the object of interest. Identify all the other objects that are interacting with that object. Draw a force vector to represent each of those interactions. You draw it from the object of interest in the direction of the force. Make the length proportional to the magnitude of the force. Now, you may not know what the magnitude of the force is, but you can possibly estimate how long it is compared to other forces. You following along with me? Okay, for example, if you've got two forces that are opposing each other and you know they're going to cancel out, you know they've got to have the same length. Okay? And then the last item is you've got to label the vector appropriately. The reason why is you're going to take that diagram, and from that diagram, you're going to write your vector equations. Do you see what I mean? Okay. So you make your table of knowns and unknowns, you do your reading and all that stuff, you label your diagram, you put your vector symbols on it, and then you go, okay, I've got to add my vectors together. All I got to do is look at my diagram. There's my vectors. You see? All right, here's my exercise for you. You are in an elevator weighing a fish. Yeah, I know, there are questions, but we'll skip those. You're weighing a fish from a hanging scale. My question for you are, what are the forces acting on the fish? Now, the scale is going to be your standard fishing scale. That is to say, you hook into the mouth of the fish and hold it up. We're not talking about the pan scale that you have over at a grocery store. Okay? So go ahead and get started working on those. Oh, by the way, the question is probably what's happening to the elevator? I don't know. That's just what you see there. Okay? I am looking at your diagrams, and most of you got a pretty good idea of what's going on. So let me show you what I did. First thing, of course, is we're going to draw a picture. So here's my picture of a fish hanging on a scale in an elevator. Okay. Then the next thing I'm going to do is I have to identify the object of interest. What's the object of interest? The fish. So let's isolate the fish. Okay. What is the fish interacting with? The scale and? No. No. It's not gravity and it's not weight. What is the fish interacting with? The earth. Okay? The earth. The object it's interacting is with the earth. Now, What that means is the scale is providing a tension force and the earth is providing a weight force. You see where I'm going here? If you can't identify an object that's providing the force, then you do not have a force. Yes? Take a look at your diagram. Isn't that the case? Which way is tension pointing?
I was wondering if the arrow above the W.
Yeah, it's an arrow above the W. What's the direction of the arrow itself? What's the direction of the weight vector? Downward. What's the direction of the tension vector? That's it. We're done. This arrow here, this thick red arrow, represents the tension vector. This is the tension vector right here. This arrow here represents that tension is a vector. Okay? It's not this arrow right here is part of the symbol. It's not the vector. This arrow right here, that's the vector. Okay, does that kind of clear that up? Okay. Yeah, because what happens is when we do our vector equation, it's going to be t as a vector and w as a vector are going to be added, subtracted, whatever you're going to do. Okay? And that's why there's no positive and negative, because the direction is in the vector. It's when we go and break it down into components that we're going to be putting in the positive and negative. Okay? Everything make sense so far? Now, as you can see, I've drawn this to scale. I've drawn this so that the tension and the weight have equal magnitude. This is assuming that there's a zero acceleration. If there's an acceleration in one direction or the other, then we have to change our scales appropriately. If it's accelerating upward, tension's going to be bigger. If it's accelerating downward, weight is going to be bigger. Okay? Here's my next exercise. I want you to make a free body diagram of this guy. I'm looking around. One moment, please. I got to check. Okay, I'm looking around, and I see you guys got kind of the right ideas, but the details are going to bite you. Okay. For example, a number of you put the tension of the rope pointing straight up, and that doesn't make sense. If the ropes are providing the tension, then which way is the tension force going to go? And the answer is it's going to go in the direction of the ropes. A number of you drew the ropes when you did your diagrams. You drew the ropes as curves. Well, how can you represent the direction of the rope, the direction of the force, if the rope itself is curved? If you're hanging on a rope, is the rope going to be slack as you're hanging there? And the answer is no. So it should look, your free body diagram should look like that, where you have weight pulling downward at the center of mass. You have the tensions from his hands pulling up in the direction of the ropes. And so what you see is that T1 and T2, because we do not know that they are the identical tensions. So we're going to give them subscripts. We see this is a tension and this is a tension, but this is tension 1 and this is tension 2. Why do we do that? Because when I go into my equation and I do my addition, let's say I add all these forces together, it becomes T1 plus T2 plus W equals whatever. You following along with me, guys? That's the reason why we're doing this. Because the next step would be to find the components of those vectors. And now you see why it's important to put those vectors in the proper directions. One other thing to take a look at, and here's kind of my checks. We see W is pointing straight down. So that means the upward components of T1 and T2 must both be pointing upward, and the sum of those two upward components must be the same. But there's one more detail, and this is where it would bite me, is T1 and T2 are also pulling sideways. T1 is pulling to the left, T2 is pointing to the right. If the ape is not accelerating, then those two have to cancel each other out, don't they? Which means probably T1 is probably too short. You see what I mean? Now, we would find this out as we actually do our calculations, but the angles we would be able to see from the diagram, yes? All right, I got another exercise for you. Oh, wannabe aviators. What are the forces on this airplane flying at a constant altitude and at a constant airspeed? The airplane is flying from the right to the left. If you're curious, this is a solar-powered airplane. Okay, looking at this picture of this airplane, we see that the airplane is moving from the right to the left. Okay, if you're curious, how do I know? Take a look at this right here. That's the airfoil for the wing. And so this is the leading edge, and that's the trailing edge. So the airplane is moving to the left. All right. So what are the forces acting? What are the forces acting on the airplane? Well, better question is, what are the objects acting on the airplane? We have the Earth is acting on the airplane. That's causing the airplane to get pulled downward due to weight. So we've got weight pulling downward. But if weight is pulling downward, something's got to be pushing back up. That force is called lift, and that's provided by the air pushing on the wings. See, you've got to have an agent for this interaction. What's causing the airplane to go forward? Well, it's a modified form of lift. It's the propellers spinning through the air. There's going to be a lift provided on those propellers, but it happens to be pushing to the left. And the name for that is called thrust. For a propeller airplane, it's the propellers being lifted. For a jet airplane, it's the push of the gas being thrown out the back. And then the last thing is, well, anybody who's ever stuck their hands out the window while you're driving in a car, you feel the wind pushing back. That air resistance is called drag. And so our four forces of aviation, which if you're going to fly, you are going to memorize these, is lift, thrust, drag, and weight. And so we have W for weight, TH for thrust, so we don't mix it up with tension. We've got L for lift and D for drag. All right, that's what you're going to see on your standard aerodynamics model. Question? Would the force of what? Would the force of thrust be greater than the force of drag? The answer is not necessarily. Okay, if the airplane is traveling at a constant altitude and a constant speed, what's its acceleration? 0. So if it has 0 acceleration, what should its net force be? What should all of the forces added together be? 0. Remember, a net force of 0 does not mean an absence of forces. It means that the forces all cancel out. Can you have the thrust be bigger than the drag? Yes, you can. If you want to go faster, you increase the thrust, you're going to accelerate forward. You're also going to then increase your lift, so you're going to start accelerating upward. You're also going to burn more fuel, which means your weight goes down, which accelerates you upward even more. But the faster you go, the more air resistance you're going to get, so that's going to increase your drag, so you're going to balance back out again. What if you want to slow down? If you want to slow down, you decrease your thrust. Now drag is bigger than your thrust, you're going to slow down. You following along? So your question is this the case? The answer is depends, because flying is balancing those four forces. Do I want to accelerate downward? Yes, I want to reduce my lift. How do I reduce lift? By increasing drag or decreasing thrust. You following along? Okay, that's why we have a flight school here on campus. All right, I got another question. I got another one for you, and this will finish it up. What are the forces on the human cannonball while she's flying? So what are the forces acting on the human cannonball? Name one. Yes? Weight, yes, because the Earth is acting on her, pulling her downward. So I'm correct. Okay, there. What else? Yes? Drag, air resistance. She's moving through the air. So therefore, she's going to have air resistance pushing against her. What else? Thrust. Provided by what? By what? She is the cannonball. The cannon. Thrust provided by the cannon. Is she in contact with the cannon? Then how is the cannon providing thrust? It's a serious question, because here's the thing. Remember, you have to identify the objects interacting with the body. And what's interacting with her is the air, providing air resistance, and the planet, which is providing gravity, and nothing else. Nothing else is interacting with her. Okay? There's weight, there's air resistance, and nothing else. Of course, now you're sitting there going, well, wait a minute. How is she able to keep moving? Yes? Yes? No, because momentum is not a force. Momentum is not a force. If we take a look, we see weight is changing the direction of her motion. We see that drag is slowing her down. But other than that, what's keeping her going? And this is one of the things we need to overcome. The idea that you have to have a force to have an object moving. The reason why she keeps going is because there's no reason for her not to keep going. You take a bowling ball, roll it down the lane, what keeps the bowling ball moving? The answer is nothing. The bowling ball keeps moving because nothing is stopping it from moving, at least not until it gets to the end of the lane. You following along? Okay. You see, if there's no force opposing it, then what happens to does the acceleration change? Well, we'll talk more about that later on. So let's go ahead and call this morning. Remember, we have our test on Monday. So I will see you guys on Monday. Thank you.